Okay, it's time for us to get started. Hello, ladies and gentlemen. Thank you for joining us today in Kemet's Design It Day. We're very glad to see you here with us today. My name is David Adib, and I am Kemet's Senior Technical Marketing Engineer here in Florida. The topic of this session is conducted emissions, and our speaker for this topic for today is Leanna Weekly. Leanna is one of Kemet's field application engineers, and this session is scheduled for 30 minutes, a total of 30 minutes. And during this session, you can send us your questions using the Q&A function in your Zoom window. We ask that you please do not use the chat function. We will try to get to as many questions at the end of our session as time permits. With that said, I'll turn it over to Leanna. Leanna, please go ahead and get started. Thank you.
Thanks, David. Hi, everyone. As David said, there we go. As David said, today we'll be discussing conducted emissions, a little bit about me. I've been an FAE with Kemet for about 3 years, a little bit more. And I do have an electrical engineering degree from the University of Kentucky. So yes, I do enjoy basketball. And I am based in the Detroit area, so very automotive focused. So I do represent Kemet on the AEC Council. So just a little bit about me before we get started. So let's jump on in. Today we're talking, as I said, about conducted emissions. Which is a type of electromagnetic interference, or EMI. So there are two different types of electromagnetic interference. One is radiated and the other is conducted. Radiated, you might think of an antenna or something like that. So you get your noise through the air. And then conducted noise, which is what we're going to be, discussing today, is noise that couples on a conductor. So, your power line or a trace on your board. So a way to mitigate conducted emissions is through chokes. So we're going to discuss a little bit about chokes and their design and characteristics. There are a lot of applications for chokes, also known as AC line filters. So everything from chargers, power supplies, smartphones, all the way down to solar inverters and smart meters. Some of the circuits include switching power supplies and, of course, EMI filters. So here we have an input filter for a power supply. And you'll see that L1 and L2 circled in red are common mode filters. So there are two types of noise, common mode and something called differential mode or normal mode. So common mode noise, which is what these filters or chokes are helping to attenuate, is noise where the currents are in the same direction. So on your signal on your ground line or your line and neutral line, you would have current going the same way, so in the same direction, hence common mode. The other type of noise would be differential or normal mode. And that type of noise is in the same direction as your power supply current. So it'd kind of go around like this. Which means that your currents would be going in opposite directions or different directions for differential mode. So those are the two types of noise, and for these types of noise, there are two different types of chokes. So the first type that we'll talk about is normal mode. Normal mode chokes consist of a magnetic core, and you have a coiled wire around it. These will be in line with your line or your signal. So you would have one per line. And as the way it works, as your current flows through your core or flows through this wire, you will create a magnetic flux. So that magnetic flux occurs in the coil and creates an impedance. And that impedance is what kind of chokes out that noise that it's seeing. So that's how normal mode chokes work. Common mode chokes, we'll skip over to this picture here. Remember, common mode noise, it has common currents in the same direction. So these will be across the lines instead of in series with your line. So there will be two windings, one on each side. The number of turns, of course, will vary based on what the choke is, but there will be the same number of turns on each side. So what happens is just like your normal mode choke, you have your current coming in. And as the current comes into each side, a magnetic flux is created, these dotted green arrows here. And those will add on to each other. So that creates, this big impedance that will choke out your unwanted common mode noise. Now, since these common mode chokes are across your lines, they will see your normal current or the signal current that you don't want to attenuate. So to show you how this kind of works, that current should pass through a common mode choke safely. So if you see here, this is the exact same layout as here. You have two different windings on your magnetic core. But remember, for differential or normal mode current, it's in opposite directions or different directions. So that means that the flux that's created on each side will oppose one another and cancel each other out. And then your impedance will be 0, and that current is free to pass. So these common mode chokes should only impact your common mode noise. Now there is something called a leakage flux that will occur that could impede your normal mode current, but we'll call this an ideal choke, and we'll say, that there is no impedance for your normal mode current for this, just to make it a little simpler. So there are two different types of magnetic material. One is hard and one is soft. And so when you magnetize these materials, they act a bit differently. So if you have a hard magnetic material, once you magnetize it through putting current around these coils. If you have a hard magnetic material, if you open that circuit and you take the current off of that magnet, it remains magnetized. So this is a permanent magnet, and that's not really what you want for a choke. That's why we use soft magnetic material for common mode chokes and differential mode chokes. So what happens with these is when you remove that current from your windings, your magnetic flux actually is lost. Now, soft magnetic materials also have a different impedance with each frequency, and we'll go into that here in a second. But that impedance that's created at different frequencies helps to suppress your noise. And that's why it's a good material to use for chokes. So speaking of magnetic materials, Kemet does produce all of our magnetic materials from the powder stage. So we have a lot of different materials that we use and do a lot of custom designs. And we're going to look at a few of these, 3 of them. So let's take a look. This is a frequency and impedance chart. We'll first look at this orange line, and this is our 10H type material, and our SC series is made out of it. And you can see, you've got an impedance up here, it peaks here and goes back down at different frequencies. Now, if we move to a 15H material, we can increase that impedance by 30%. And then if we move again to the S18H material, we can increase that again by 35% more. So a big impact on your performance of your choke will be the material that is used. So with these three materials, you can see right here, somewhere between 0.1 and 1 megahertz is kind of where they top out the highest impedance. And that would be the range of frequencies that you would look to use these chokes at. Now, if you had a frequency or you had noise at a frequency down here or up here in your high frequency range, then these materials wouldn't do too much for you. So you want a high impedance so that you can choke out all of that unwanted noise. So we talked about common mode and differential mode noise, or chokes, sorry. We also have something called a dual mode choke, which is a hybrid design. So in a conventional design, let's say it's an EMI filter, you would have a common mode choke, which again goes across your lines to cancel out your common mode noise. And then you'd have two differential mode chokes, one on each line, to help attenuate with your differential or normal mode. They're the same thing, type noise. So what a dual mode choke does is it allows you to replace all three of these elements with one single choke core. So you're able to reduce footprint, save on space, and reduce the number of parts that are on your bomb. So this is our hybrid or dual mode choke. And remember I mentioned earlier when I was talking about common mode chokes, how there's something called a leakage flux. And that leakage flux can impede your normal mode current. So what we've done to create these dual mode chokes is we've optimized that leakage current leakage flux in order to produce a differential mode noise filtering within the same core. So I'm going to compare this to a flat wired common mode choke just because it has kind of a similar structure. So flat wire common mode choke, it has this square is the core, and then you have these flat wire windings here. And as you can see here, it does have quite a bit of leakage flux, which could help attenuate your normal mode noise. But this also is causing interference in your outer field in other parts of your circuit, because this kind of just radiating out that leakage flux is. Now let's look at our dual mode choke, and this is how it's designed. It's a bit more complicated. So this outer part, as well as this center cross section, is the core. So this core allows for better insulation of that leakage flux. And then the windings are here. So it's just like a common mode choke. It has two different windings, just like your flat wire common mode choke up here, that go around the core. The only difference is the shape of the core. And of course, there'll be different windings and different wires used, but in general, that's the difference, is the core shape. So this suppresses the leakage flux, so that stays inside. It doesn't cause interference into the rest of your circuit. So that's the main positive about this. Now there is a downside, and that would be your stray capacitance. A flat wire common mode choke would have less straight capacitance in this dual mode choke. One reasoning is this is round wire that's being used versus flat wire. And these are smaller windings here. So you have several windings on top of each other versus a long flat winding, and you have fewer of them. So this over here just shows, you know, your flux lines. You would have your common mode. Imagine this over here. You'd have your common mode flux lines going this way. And then the normal mode or differential mode flux lines would be kind of separated into quadrants. So you can kind of see they kind of go like this, or this, sorry, and they cancel each other out in this center part here. So that's kind of how the flux lines work. These dual mode chokes are for lower currents, so up to about 3 amps. And the differential inductance is around 2 times that of a conventional common mode choke. So it has really been optimized to help with that normal or differential mode noise. So let's take a look at a comparison. This is an example of a product that is going through EMI testing, and you're using a common mode choke, and you're having a little trouble in this area. You can see you're above the limit. So you decide to put 2 differential mode chokes in your design. And you can see that it really attenuated the noise. So it looks like you're passing, you might be a little bit above still, but you've greatly brought down the noise level in this area. Now let's compare that to a dual mode or hybrid choke. So we've replaced all 3 of these parts with just 1 hybrid choke coil. And you can compare the 2 outcomes from the EMC testing, and they are very, very similar. So here you can see how you can replace 3 of these products with just 1, save board space, and shrink your design. So just like we do customized solutions for common mode and differential mode chokes, we can do customer optimized solutions for hybrid choke coils as well. This is just an example of that. So an example of one of these chokes. So here you can see what the common mode and the differential mode inductances are. And over on the right, you can see the frequency characteristics, both the inductance and impedance of this coil for common mode and differential mode. So this is just an example of one of the chokes that we are capable of producing. So that's all I had for chokes. We will now move on to EMI cores. So just like chokes, EMI cores are used to help with noise that's generated in electronic circuits. So it will filter out noise. Here's another example where before using this core, you had several issues over here where you were above the limit. And then after using the core, you greatly reduce the amount of noise you were seeing. So there are a lot of different types of EMI cores. There are over 100 types and variations available. Solid, snap-on, snail shape, depending on what you need. They will come in, they are ferrite cores. They will come in there are 2 types of ferrite or core material, manganese zinc and nickel zinc, based on what frequency you are looking at. So a core would be used on a power cord or a wiring harness, an actual wire. And there are lots of different defining parameters when you're looking at cores, one of which is shape and dimension. There's something called shape factor when you're looking at cores. You can have the exact same material in a core and have different impedance values show up based on that shape. In those mounting versions that I talked about earlier, the solid core, the snap-on, the snail-shaped, those will all change your shape and dimension and impact, the impedance that you would get with those parts. So just like the chokes that we talked about, you would look at cores. You would target a frequency and whatever impedance, you want a high impedance at that frequency that you're targeting. Now, your impedance will increase by squaring the number of turns that you put through the core. So if I have 2 turns here, and you can see the difference between 1 turn and 2 turns on the chart as well. So at 10 megahertz, what is this one? About 50 ohms, that shoots up to about 200 ohms just by turning your cords through the core one more time. And then that increases even more with more turns. So if you do need more impedance, you can just turn your cord through the core several more times. And this is just an example with one of our ESD-R type parts. Now, EMI cores, just like chokes, can be used for both differential mode and common mode noise. So say I have a wiring harness and I have common mode noise going on. I can put the choke on both my signal and ground wires, or, so it would go around all of your wires. Whereas if you have differential mode noise, you could put one on each. So just like a choke, that's kind of how you would use these. So like I said, just like chokes again, the frequency range of that the product can handle, or where your impedance is higher, is highly dependent on the material. So manganese zinc is used for lower AM band type frequencies, whereas nickel zinc is used for higher frequency FM band type ranges. And then at the end here, we've just kind of put together a brief step-by-step guide on, selection of common mode chokes and cores, where to start, what to look for, and what information you need when you're designing in a common mode. So we've based this on this equation for inductance. So this goes into, the number of turns, the size of your core, relative permeability, things like that as well. And we've used that to kind of make these steps for an engineer to follow, what to look for, what parameters you need to have when you are designing in a choke. Now, I'm not going to go through this step by step because it is kind of a busy slide, and there are a lot of steps here. But as you could tell, as I was going through the presentation, one of the main things that you need is what frequency range are you targeting? And then you need to find a choke or a core that has a high impedance at that frequency range so that you can attenuate that noise. Now, I mentioned several times throughout this training as well that we do have, custom and optimized type cores. Just be aware that there are trade-offs with that. You can't get it all. I mean, it is physics. So just be aware, but if you do have any questions or you're looking for a specific custom type device, please feel free to come to us. All right. And that's all I had for you. Are there any questions? I think I saw a couple popping up.
Thank you, Leanna. Yes, we do actually have some questions that are coming in right now. First question says, in general, what are the MOQs for the custom chokes?
It would depend on the core material and size and shape and what we have. I'm not sure on an exact number or minimum order quantity, but we can definitely get back to you if you want to reach out to me. I can get you a number.
Okay. And the next question says, you mentioned that the dual mode choke has higher stray capacitance. Is it in the range of single percentage or several times of parasitic capacitance, I think is what he means. Can you find the parasitic values in data sheets?
I don't believe that we have the parasitic values in data sheets, but a lot of these chokes are, you know, customer optimized or custom designs. So that's something we can work with you on, and you know that value would depend on the exact part itself, depending on, you know, how many windings there were and things like that.
Okay, and these are all the questions that I have received so far. Once again, thank you, Leanna, for this presentation, and thank you to all of our audience for attending and joining us today. Until next time, I wish you all a good day, and take care, and goodbye. See you next time.
Thank you all very much.
Thank you. Bye-bye.